In Part 6 of Lecture 4, we will discuss threads in Linux. A process, or task, in Linux is represented by a task struct data structure. The task struct data structure contains information in a number of categories. State. It lists the execution state of the process, whether it's executing, ready, suspended, stopped, or zombie. This is going to be described subsequently. Scheduling information. Information needed by Linux to schedule processes. A process can be normal or real-time and has a priority. Real-time processes are scheduled before normal processes, and within each category, relative priorities can be used. A counter keeps track of the amount of time a process is allowed to execute. Identifiers. Each process has a unique process identifier and also has user and group identifiers. A group identifier is used to assign resource access privileges to a group of processes. Interprocess communication. Linux supports the IPC mechanisms found in Unix SVR4, as will be described in Lecture 6. Links. Each process includes a link to its parent process, links to its siblings, in other words, processes with the same parent, and links to all of its children. Times and timers includes process creation time and the amount of processor time so far consumed by the process. A process may also have associated one or more interval timers. A process defines an interval timer by means of a system call. As a result, a signal is sent to the process when the timer expires. A timer may be single-use or periodic. File system includes pointers to any files opened by the process, as well as pointers to the current and root directories for this process. Address space defines the virtual address space assigned to this process. Processor-specific context, the registers and stack information that constitute the context of this process. The figure on the slide shows the execution states of a Linux process. These are as follows. Running corresponds to two states. A running process is either executing or it is ready to execute. Interruptible, a blocked state in which the process is waiting for an event, such as the end of an input-output operation, the availability of a resource, or a signal from another process. Uninterruptible, another blocked process. The difference between the interruptible state is that in this state, a process is waiting directly on hardware conditions and therefore will not handle any signals. Stopped. The process has been halted and can only resume by positive action from another process. For example, a process that is being debugged can be put into a stopped state. Zombie. The process has been terminated, but for some reason still must have its task structure in the process table. Traditional Unix systems support a single thread of execution per process, while modern Unix systems typically provide support for multiple kernel-level threads per process. As with traditional Unix systems, older versions of the Linux kernel offered no support for multi-threading. Instead, applications would need to be written with a set of user-level library functions, the most popular of which is known as pthread or POSIX thread libraries, with all of the threads mapping into a single kernel-level process. We have seen that modern versions of Unix offer kernel-level threads. Linux provides a unique solution in that it does not recognize a distinction between threads and processes. using a mechanism similar to the lightweight processes of Solaris. User-level threads are mapped into kernel-level processes. Multiple user-level threads that constitute a single user-level process are mapped into Linux kernel-level processes that share the same group identifier. This enables these processes to share resources such as files and memory, and to avoid the need for a context switch when the scheduler switches among processes in the same group. A new process is created in Linux by copying the attributes of the current process. A new process can be cloned so that it shares resources such as files, signal handlers, and virtual memory. When the two processes share the same virtual memory, they function as threads within a single process. However, no separate type of data structure is defined for a thread. In place of the usual fork command, processes are created in Linux using the clone command. This command includes a set of flags as arguments, as defined in a table we've seen earlier. The traditional fork system call is implemented by Linux as a clone system call, with all of the clone flags cleared. When the Linux kernel performs a switch from one process to another, it checks whether the address of the page directory of the current process is the same as that of the to-be-scheduled process. If they are, then they are sharing the same address space, so that a context switch is basically just a jump from one location of code to another location of code. Although cloned processes that are part of the same process group can share the same memory space, they cannot share the same user stacks. Thus, the clone call creates separate stack spaces for each process. Associated with each process in Linux are a set of namespaces. A namespace enables a process, or multiple processes that share the same namespace, to have a different view of the system than other processes that have other associated namespaces. One of the overall goals of namespaces is to support the implementation of control groups, or C groups, formerly known as containers, a tool for lightweight virtualization as well as other purposes that provides a process or group of processes with the illusion that they are the only processes on the system. Thus, the C group is a form of virtual machine. There are currently 6 namespaces in Linux: MNT, PID, NET, IPC, UTS, and user. Namespaces are created by the clone system call, which gets as a parameter one of the 6 namespaces clone flags: clone new NS, clone new PID, clone new NET, clone new IPC, clone new UTS, and clone new user. A process can also create a namespace with the unshare system call with one of these flags. As opposed to clone, a process is not created in such a case. Only a new namespace is created, which is attached to the calling process.